Okay, sorry guys, sorry for the breaking session. So we had to get the meeting recording for those that are not available. So I'll just take it one more time. So our speaker for today is Zainab Officer, and she will be taking us on the efficiency as the principle in machine learning and a bit about Zainab. She's a penultimate computer science student with a focus on data science and machine learning, who has across consulting, finance, and technology, and co-works on machine learning integration and deployment as an engineer at Russell. Our work explores how to make machine learning practical and efficient in low resource settings. So without much ado, I'll just like to transfer the mic to Zainab. I believe she's on the call right now.
Yeah, hi, can you guys hear me? Um,
Yes, we can hear you, but I don't think it's really audible.
mm, Give me a minute. I'm trying to, when I share my screen, just once. Okay, can you guys hear me?
Yes, we can. Clearly.
Okay, so thank you for the introduction. So I'll be, yeah, like you said, it's an hour session. So I hope to finish in like 45 minutes so we can use the remaining time for questions. So yeah, I'll be talking about something interesting, which is efficiency. Mostly efficiency, but this is just like a cute way to put it, like efficiency as a principle in machine learning. I mean, we're going to talk a bit about that, like why I decided to frame the topic as like that rather, but also mostly about efficiency and how we should approach efficiency, then how to approach machine learning better if we're thinking or if we're coming from that mindset. So I'm sure that we've pretty much heard about efficiency at some point or the other. So the things that we'll be looking through are trying to reframe the way we think about efficiency. I'm personally very interested or passionate about efficiency in general, efficiency as a human being, efficiency of everything. So it's just very interesting that it's a whole thing in machine learning. I mean, it has to be. Then also optimization, because most times when we talk about efficiency, we talk about optimization, then training techniques, like smarter training techniques, some of these things we've heard of before, but just like conceptualizing them, then building efficient models, and finally key takeaways, then question and answer. So, like I said, I'm reframing efficiencies to generally what do we mean by efficiency? I just had to insert the definition of the general of the I just had to insert the general definition of efficiency rather. Because like I said, I'm very passionate about efficiency and it just drives down when it's ML. It's the same thing. We're just trying to achieve a better result. Or I would say the desired result, not a better result, because the results each person wants will typically vary. And we're trying to do that without wasting effort, time, or resources generally, because the world doesn't have abundant resources, so we have to manage them. And in machine learning, it's the same thing. We're trying to train and run models using less compute memory time because we know that these are the things that we typically talk about when we mention efficiency in machine learning. So typically, when we think about efficiency, if you're not on this table, that's very fine. But when we think about efficiency, we think about efficiency as optimizing it after the model works, or even sometimes just getting the model to work. Because I mean, I can say that we are working in low resource setting. Maybe assume that meaning that most times we have to always think of how to manage what we have, which is nice. But then I would come to what I think that we should think of efficiency as, rather than the saving grace of, oh, I can just use this technique because this doesn't work anyway. So like I said, make it fit on edge devices, because we know that this model is really large and I'm trying to use it on a device with like maybe 8 gig or something like that. Then using quantization or pruning, or just making it run faster or cheaper, not really because we are grounding it in the idea that we should always manage resources, but maybe because of other reasons, like, oh, I can't afford this right now, or I don't have the GPU for this. I mean, even if we have the GPU for it, or the compute for it rather. So I'll just come to that here. So before I move on to talk about how I think we should approach efficiency, I'm going to talk about how efficiency is in one thing. I think we pretty much have an idea about this, that when we're talking about efficiency, we're talking in terms of time, in terms of memory, in terms of compute, in terms of data. For time, we're trying to see how fast we can train or infer. Um, for memory, we're trying to see, will it fit in a RAM, or will it fit in a VRAM? Like I said, or looking at this last column by the right, we know that for time, every user, or if we've heard of like users typically, or user experience, users will be very impatient if we say there's a model and it's taking like 5 minutes to run. They really do not care about that. For memory, the same thing. For compute, how much hardware slash energy is required. I think there's some point in my slides where we talk about flops better, but compute is actually, all these things drill down to energy. We're trying to maximize what we have. Also for data, how many labeled samples are needed. And something to note is, generally one dimension would really improve without impacting the other. So we would always have to work with trade-offs. So if we are trying to maximize the time, maybe we would have to sacrifice some accuracy or something like that. But there would always be a trade-off. It just depends on your use case or what problem you're trying to solve. So I have this slide here that talks about generalization versus efficiency. And I'm using generalization, or the idea, which is the idea rather, that a model should perform well on unseen or new data as a reference point, because I believe every ML engineer already builds for this. I mean, instinctively, we'll always address generalization as, or before training starts, we plan for it upfront using things like data splits, regularization rather, early stopping. Efficiency, on the other hand, like I said in my first slide, is usually addressed, or typically addressed after training. So we're trying to, more like deleting weights to shrink the model, or converting weights from 32 bits to 8 bits to save memory and speed up inference, or even last minute tweaks so the model meets a response time target. So the main thing I'm saying here is, we can design for efficiency from the jump the way we, or we can think about efficiency from the jump the way we think about generalization from the jump, which is the way we would approach every other thing in my slide moving forward. So yeah, like I said earlier, thinking of efficiency as a design principle, if we can put it that way. So trying to pick the right model size before you start training, even if you have all the compute in the world, training with Sorry, can you guys hear me? Okay, sorry.
Yes, yes.
You lost me for a bit. Okay, so I was saying the ways we can think about efficiency from the jump to optimizing for total cost to generally thinking about everything that we need for the model from the beginning. So not just maybe not just the time, but also the compute and every other metric from the jump. Tracking efficiency metrics alongside accuracy. So typically we track accuracy, but we can also like track efficiency metrics. I think we're going to speak more about this. Okay, so let's look at optimization, like I said earlier. So yeah, now we're going into efficiency itself properly. We already established that whenever we are training models or whenever we are doing machine learning, we should think about efficiency from the beginning or how to use or how to maximize resources from the beginning before we run into trouble, or rather as a tool to avoid trouble. So where do all the resources go to in machine learning generally? So usually when we think of optimization, we think of these four steps. We have the forward and backward cost. And as we know, forward pass is like one run through the model to get predictions. Backward propagation is basically the same amount, or we do the same amount of math for backward propagation to get the gradient. And together they use roughly twice of the math.
Otherwise, I think she's having a network issue. Join us back shortly. Um, Zainab, in case you are talking, you are muted.
Oh wow. Okay. Wow, I'm sorry. Okay, so I just started speaking to this slide again. So I'm just going to do that again. All right. So what I was saying basically is I'd said earlier that everything we pay for in terms of training happens in this four-step loop. So you guys get what I mean by paying for, meaning that cost or like everything we pay for basically, or every resource we use basically in training happens in this four-step loop, which is forward pass, loss, back propagation, and updates. And as we know, the forward pass is when we run through the network and we produce a prediction, while the loss is when we compare that prediction with the truth label and get a number that tells us how wrong we are. For the backward propagation, that's when we run through the network or run the network rather backwards to compute gradients. And this just tells us how much each weight contributed to the error that we have, while the update is when we nudge the weights using the gradients we already have, our learning rates, which is this, and whatever optimizer rule we have picked, which would come to, right? So most of, or how much we spend or how much compute would typically depend on how this step works, right? Okay, so this is me just trying to ground what I just said in quantity so you guys can kind of see how that applies. So like I said earlier, training cost typically equals the number of iterations multiplied by the amount of math in each iteration. So I think we all know what iterations are, which are like the training steps or batches. And just to mention also, flops are, or flops by iteration, are the floating point operations or the raw calculations that are done in one forward plus backward pass rather. So let's take a common image classification model, which will be ResNet 50 on the ImageNet data set. So one training step. Okay, as I say, one training step for this model will be about 1.5 billion flops, and a full 90 epoch run will be about, you don't have to follow with like what I'm saying. I'm just trying to get to a particular point, which we'd get soon. So a full 90 epoch run will be about 1.3 million steps. And if you multiply those, you get about 2 times 10 raised by 15 flops total. So if our GPU is using about 300 watts, that is about 1.7 megawatt hours of electricity, which, I mean, I think we can use that for like a week. I mean, in terms of electricity, right? So the bottom line is, if we can shrink either side of the formula that we just saw above, that is fewer steps to converge or fewer flops per step, will cut the cost right away. So this means optimizer choice, optimizer choice, let's keep it that way, is very important, or could be like our first step in terms of efficiency. So let me go back in case anyone is lost. So first we looked at the 4 steps, right? Then we looked at what those 4 steps do. Then I tried to analyze how much money, or we put it in terms of electricity, how much we can spend. So we're saying that if we can reduce what is basically happening in any of these steps, then it's a great way to approach efficiency. Okay, so now we can go to practical optimizer levers, or practical optimization levers, if we can put it that way. Not mine. So on the last slide, or on the last 2 slides, we learned 2 major things. Like I said, we learned that the training loop is where all the resources disappear, and total cost is iterations times the work by iteration, which is what we had here. So everything that we're looking at here are ways to shrink one side of that equation that we saw, and all of them sorry, if you guys cannot hear me, can you guys like, or can someone speak or something? So typically I don't continue speaking and realize that you guys cannot hear me. But I'm going to assume that you guys can hear me right now. Or is it me that can hear you guys? I don't know. Is anyone speaking?
We can hear you. Can hear you.
Okay. I don't know if you guys heard anything here, but I'm just going to continue. My network is a bit wishy-washy today. So please, if you guys cannot hear me, I'm not on the screen, so I can't like raise my hands or anything. But if you guys can just say or send a text that you can't hear me or just say something, it'll be very helpful. Okay, so I was speaking about the this slide. I don't know if you guys heard me here, but again, I'm just going to take it again. Hopefully, we don't exceed the 45 minutes that I'm trying to stick to. What I said basically here was that the last two slides we looked at the training loop and we looked at it, we tried to quantify how much we spend in that training loop. And now we're trying to, so basically we've agreed that if we can reduce anything that's happening in the training loop, we can save cost. So how can we do that? Yeah, so these are some ways that we can do that. Adaptive optimizers, I'm sure some of us have heard of this before. And what they basically just do is adjust learning rates separately for every weight. So that way they reach the target loss in 2 to 3 times or fewer epochs. So basically we have fewer epochs. So that just reduces cost. Also mixed precision. So again, we've probably heard of this before, but if we run the math in a lesser bits, like 16 bits rather than 32, it also reduces the weight or the amount of math that we have to do, if I can put it that way. I'm just trying to simplify it. So for gradient checkpointing, there are other methods, by the way. I just decided to go with these three that are probably that we have most likely heard of. So for gradient checkpointing, instead of storing every activation in the back propagation, we keep only a few and recompute the rest on the fly. That way, we save memory. So these are ways that we obviously don't deal with the math typically when we are coding, but just knowing that if we are doing these particular things, we're trying to save cost based on what we just learned earlier, right? So yeah, like I said, these decisions happen inside the learning loop before any model compression, because I know that we most likely have heard of things like LoRa or things like maybe I'm trying to remember something right now, few short learning or just other things that we generally use when we talk about efficiency, right? So all those things we are going to talk about them, but I just decided to start with optimization. So we see that, oh, we can start with this and we can still we can still move on to in terms of data or in terms of the other ways or even the models that we choose. But we're going to speak about all of that. So this is just like a case study to solidify everything that we have been learning earlier, right? So as we can see, SGD plus step LR needs 90 epochs, and this runs for 72 hours on 8. Sorry, that was a mistake. This runs for 72 hours.
Hello?
So for Adam W and cosine decay, still using the same model, but with a different optimizer and a different learning rate schedule. So cosine in this case, it cuts the number of epochs from 90 to 40. And as you can see, the wall clock to about 28 hours. Then let's look at LAM plus FP16. We can see it cuts the number of epochs to about 30 and we still see 18 hours. So this just shows how changing your optimizer or the scheduler that you use, how that can affect your performance and how much time or how many epochs, or generally how that just affects what we saw earlier, which is this loop, the training loop. So if anything that or if we're going to take anything, I don't know, my next one was a bit, so I don't know, not to confuse you guys. If we're going to take anything from this section, can you hear me? Oh. Can you hear me? I'll just
Yes,
Yeah.
we
proceed.
can
If
hear
we're
you.
going to take anything from the thank you. If we're going to take anything from the section that we just saw, it is that we typically already use optimizers. We already change. Sometimes we use like SGD, then SGD is probably not giving us like the best performance. Then we switch to Adam, and that's not giving us like the best performance. We switch to Adam W, or we switch our learning rate. I would usually see like we'll see changes in our model's output or the results we get, sometimes good, sometimes bad, but we usually do not know what is happening behind the scene when we change our learning rate or when we change our optimizer, if we can even reduce the number of epochs because we've already changed our learning rate. But basically, like I said, all of it comes down to this training loop and what we are doing with the training loop. So if we understand how the training loop works properly and we understand what these optimizers do, we would be able to build models way more efficiently before we even think in terms of smarter training techniques, which is the next thing that we'll be talking about. So yeah, why go beyond the optimizer? Maybe because they are boring, but yeah. Okay, so like I said, optimizer choice cuts iterations. We already saw that. Also, but smarter training rather cuts the constant factors. So what we're talking about right now is smarter training techniques. We already looked at optimizer that we can see what optimizers can do, but there are also other ways that we can be more efficient or we can train more efficiently.
We can't hear you.
Can you guys hear me? These guys are frustrating me.
Yes, we can.
Yes, we can hear you now.
Okay, so I guess you guys heard this. So I was talking about schedulers and regularization tips and what that does since we already looked at optimizers. So again, we're still trying to lower the number of passes that we make over the data. And these four, if I can call them, these four tweaks, we do that without us needing to touch the model architecture. We're still going to come to the model architecture. But again, I'm sure you guys most likely have heard of things like cosine decay and warm up, one cycle policy, label smoothing, etc. And what they, you probably do not know what they do rather, but you have used them before and you see how they affect performance. So I'm just going to speak a bit about this. So for cosine decay, or let me talk about the one cycle policy, which is when the learning rates, or when we make the learning rates rise quickly to a peak.
Can't hear you.
You know what? You guys should give me 2 minutes. Let me change my internet. This is terrible.
Right.
Okay, I'm back. So yeah, I'll just go over this again quickly. So for cosine decay, we most likely heard of cosine decay before, and just like the name cosine, so we know like the cosine plot or the cosine graph, if I can say that. There's also a trick around the learning rate, right? So again, we're trying to find the smartest way to train. So instead of dropping the learning rate in big steps, maybe saying, oh, from this to, I don't want to use any value, so I'll just leave that. So we let it slide down smoothly in a cosine curve. So we know what a cosine curve looks like. So typically what that means is that we would still get the same accuracy, but we'll get it in about 15 to 30% fewer epochs compared to the old step decay where we go from like one step to another step. Right. So another one is this label smoothing, which is when we don't let the model become 100% confident in the correct class to soften the target slightly. So again, all of these are just steps that save epoch. So that's another thing that we can try to save. So that we don't train with like maybe 100, or rather than train with like 100 or 200 epochs. So we train with lesser epochs. So let's look at data-centric shortcuts or ways that we can also work around this. So early stopping by plateau, I'm sure we've heard of this before, which is when we watch the validation accuracy every epoch, and once it stops improving for like a few checkpoints, we call training rather than just continuously training. And in practice, we know that this generally helps us um, train faster, I'll put it that way, because rather than just training, and then looking at how it performs, we can just have early stopping, and once the model stops learning, we move on. There's also progressive image sizing, which is where we start the first part of training rather with smaller images. Let's say 128 pixel by 128 pixel, then we switch to full resolution, and we know that smaller images means less computation per batch. So typically we should save around 25% of the total flops. So I put all of these metrics, or I try to quantify it like this in my slides, so that we know that, oh, we use these techniques or these shortcuts in our day-to-day, but this is actually what they are doing, or this is what they are capable of doing. If we do computer vision, most likely heard of augmentation and data augmentation techniques like cut mix up, which are techniques that we use to shuffle or blend images on the fly, basically as they're being fed into the model, and they typically boost the final accuracy and just reduce how many unique examples we need for the model. So rather than feeding the model with maybe 10,000, that's a large number, but 10,000 unique images, we can just feed it with less, but different. It sees the images that we give it in different ways. So that gives it like different angles rather than having to take pictures of every scenario, gather every possible type of image, right? So these four tricks I just mentioned, or these four tricks I just mentioned rather,
We stopped hearing you.
for to building efficient models. Okay, yeah. So to building efficient models, so now let's talk about what we can do regarding the models themselves. So we already looked at optimizers, we already looked at tricks around data. So now let's also talk about the models themselves. So how can we build efficient models? We know that typically we don't even train from scratch. We typically use like a pre-trained model, then just work with that. But yeah, that's kind of what I'll be talking about here. So like I said, everything we've done so far in terms of optimizer tweaks, taking smart schedulers, data tricks. I'm doing a lot of recap because I don't know what you guys may have missed at any point because of my internet. But yeah, that helps to squeeze the model. But we know that if the model or if the network itself is oversized, then we're still carrying like extra weight. So this slide or what we're about to discuss now shows models that are models that we can use depending on our use case, right? So we've most likely heard of like mobile net or DistillBert before. So mobile nets for vision, DistillBert for text, and these models, I think mobile net is very popular for running on small GPUs, which is why it's called mobile. Sorry, which is why it's called mobile, and it has under 5 million parameters. So it's very respectable when it comes to training for edge devices. Then 5 to 25 million parameters, efficient net B nots, because they're different varieties, if I can put it that way, of efficient net, right? So efficient net is also a good middle ground. It's larger than, or it's a larger network. So when data is abundant and we also want to stay memory friendly, we can use efficient nets. Another one is ResNet with 25 to 100 million parameters. ResNet typically needs more memory and compute, but many libraries and pre-trained weights exist, so that should make it easier. Then also we have ResNet 152 with over 100 million parameters, has great accuracy, but the trade-off here is it demands more hardware or energy. So again, the takeaway from all of this could be that we should not start at the top of the list and hope to compress later. So pick the smallest backbone that can meet your accuracy goal within like your memory, energy, latency limits, then apply training and compression tricks that we have covered. So yeah, parameter efficient fine tuning. I'm sure if you work with language models, would have heard this before, or would have heard parameter efficient fine tuning. So we know that typically there are large pre-trained models, and we just need to adapt those models to our own data. And fine tuning basically is expensive and needs a lot of memory and GPU time. So whenever we should always lean towards using these methods because they let us update only a tiny fraction of the parameter and still get very competitive performance. As we can see LoRa, we can see the trainable parameter 0.1 to 2% trainable of the entire model parameters. This is huge, and the memory gain is about 70 to 90%. And this is the typical accuracy drop, which is not exactly a lot, if I can put it that way. But again, I'll say it depends on the trade-off. There's always trade-off, so it just depends on what you're trying to do. So another one is prompt tuning. We can see how many percent trainable, and the memory gain is about 99%. The accuracy drop is just 1 to 2. Q LoRa also. So adapters generally cut fine-tuning cost, and there's typically not a huge accuracy loss. So that's something that we should lean into in terms of models and being efficient with models, the models that we pick rather. Also, something I was going to mention is compression after training. So after training is finished, we can also squeeze the model even further. That's after training. And as we can see what's happening with this table. Can you guys hear me?
Yes, we can.
Oh, did you guys hear the compression after training slide, or should I just go over it again?
Yeah, you have to go right again. We didn't hear that.
Okay, thank you. So I was talking about compression after training, which is after we've picked the model that we want to work with, the optimizer, scheduler, and everything we discussed earlier. Something we can also do is to compress when we're done training, and we can see the different techniques and how much they can reduce the model size, the latency gain would get, and the accuracy, like what happens with the accuracy. So this is also something that we can explore. Uh, yeah, so something else is the design time, or something that I'll call the design time efficiency checklist, which is everything we've been discussing earlier, just summarized. So match model family to target hardware, the hardware that we have, whatever we plan to work with. Plan quantization aware or mix precision training upfront, and always use adapters, what we spoke about earlier, for downstream tasks, and avoid full fine tuning, even if we have the compute, except we have a specific need for it. Um, Also have, I think I mentioned this earlier, also have metrics that we use to track efficiency, just the way we track accuracy, for example, and also documents latency alongside what I just said, alongside accuracy or the other metrics. Those two mean the same thing. Okay, so for the key takeaways, this is just a summary of everything I've said so far. I started with the optimizer. Then I went to how we can train smart and not for long. Then also, depending on the constraints we have, picking our models based on that. Then fine tuning with adapters and not the full weights. Then making sure to compress last if we need to. Okay, so I think I would take a lot of questions because I don't know where there were gaps or anything. But yeah, please ask me questions. Hopefully, my internet acts
Okay.
well.
All right. Thank you very much for that. I think that was a very insightful session. So we'll be taking few questions, three questions actually, but if time permits, maybe five. So if you have any question regarding the session or any gray areas, you can raise your hand and be brought up. Okay, Diola. Yeah, you can go. Hello, Diola, can you hear me?
I can hear you. Can you?
Yes, we can.
Hello. Right. You mentioned the advantages of using methods to
Sorry,
shorten
we can
the
hardly
model.
hear you. Your background is very loud. I don't know if you can move away from it.
Okay. Would you? Can I type it there? I think I'm in
No
the public
problem, you
place,
can.
so I don't think
No
I can
problem.
use this. Right.
Yeah, so if you have questions, right, it's you can either raise up your hand or type it so to help save time. Okay, so the question was, are there any cons to the methods that we outlined? Is there not?
Sorry, what did you say?
The question was, are there any cons to the methods that I'm taking, the methods you outlined?
Yeah, I think that generally, if you listen to what I said from the beginning, it's always a trade-off. So if you're trying to optimize for data, you'll probably be dropping or losing some maybe accuracy. So none of these methods are perfect. All of them have trade-offs. So you just have to look at your use case and decide what matters to you the most. So like none of these methods are perfect. No method is telling you, oh, you'll be able to train the shortest amount of time and get the best accuracy using the less or the minimum data possible.
All right. Thank you very much for that. So, any other question? Okay. It seems I don't know. Since we don't have any question, okay. Okay. So, if we don't have any question, then I think we'll be moving on to the next agenda. So, once again, thank you very much for that insightful session and also taking us through the technicalities and intricacies of efficiency in machine learning. I think every one of us, one way or the other, has benefited greatly from this. So, guys, we'll be rounding up the session now, right? So we've gone over the Q&A. So don't forget to follow us on our social media pages, X, on LinkedIn, and try to engage with our post all of that. We have coming events. Our next events in office house, which will be happening on Monday, which is on 30th June. We'll be speaking on building scalable machine learning infrastructure on cloud services, specifically Google Clouds. So there and don't miss it. Yeah. So we also like your feedbacks. Right? I'll be pasting the links of the feedback. We like your feedback. We like you to kind of like how what can be done to improve the session. What wonderful ideas can you give us to help better the whole thing. So I'll be pasting the link to register for the next session and also the feedback link on the chat window. So let's try to pick it from there. Right. So okay. So I think we've come to the end of the session, and I will just be giving like 1 or 2 minutes for we to copy those links, and hopefully we see you in our next session. Thank you guys for coming, and thank you very much, Zainab, for uh, that insightful session.